So our today's agenda is this. So we are going to use microwave today for appreciating what we discussed in our last session on 20th, that is last Friday. So using microwave, we are going to compare the equality and inequality of the rise and fall times in the layout of 2-input NAND gate. For first case, using equal size MOSFETs and then properly sized MOSFETs. So we are going to take the sizes of MOSFETs from our last session, and then we have chosen some practice examples for calculating on-chip area. So we have taken 3 Boolean functions. Okay, fine. So we'll first have the sizes taken from our numerical example which we took last time. So we will take CMOS 2-input NAND using equal size MOSFETs in pull-up network and pull-down network. So we will assume that we are using a 90 nanometer process. So we get L fabricated as 100 nanometers. So for equal size MOSFETs, the widths of all the MOSFETs will be 500 nanometer and length will be 100 nanometer. So we write it like this. So we have the inputs A and B here. So we can write it like this. Okay, and then we have So we go to a numerical here, and this is the proper sizing of NAND gate. So we have 375 by 100 for P1 and P2. So we have, and we have, okay. This is case 1. This is case 2. So foundry is for sure is 90 nanometer. I hope my microwind UI is visible. Is my microwind UI visible?
Yes, sir.
Zero zero 1, 1. So yes, it's an AND gate. Okay. Now we are going to see the rise time and fall times in detail. So we will consider a few more cycles. So it stabilizes. Okay. So here we are getting rise time as 2 picoseconds and fall time as 103 picoseconds. So 2,103. Okay. Now we are going to have observation table. Now we'll use the sizing 375 by 100 and 300 by 100. Okay, so here we are getting 4 and 2, that is between B and the output. Let us see. Three and two. Okay. Fine. So at least I am not happy with this conclusions. Maybe I'll see it later. No problem.
क्या बोल रहा है ये
Okay, fine. So practice examples for calculating on-chip area. A dot B plus C plus E. It is A dot B plus C dot E. Okay. So F is equal to A dot B odd with C ANDed with D odd with E whole bar now becomes A dot B whole bar ANDed with C with D plus E whole bar, which now becomes equal to A bar odd with B bar ANDed with C bar odd with d dot e whole bar now becomes equal to a bar. Okay, so you cannot simplify it any further. So now it is P1 parallel P2 in series with P3 parallel with P4 series P5. Okay, so this ORing leads to parallel, this ANDing leads to series, again this ORing leads to parallel, and this leads to series. Okay, so this will form our pull-up network, and a mirror image of this thing will be pull-down network. Okay, so all p's become n's and all parallel become series, series become parallel. So now we have n1 series n2 parallel with n3 series in bracket n4 parallel n5. This is my pull down network. Now we will convert our series parallel expressions into actual hardware. Okay. P1 parallel P2. So P1 parallel P2. This parallel combination is in series. So this parallel combination is in series with P3 parallel P4 series P5 is in series with P3 parallel. This is P3 in parallel with P4 series P5. This is my pull-up network. Okay, so P1 parallel P2 in series with P3 parallel P4 series P5. So now we can give the notations. They are all PMOSes. Okay, and they will be having the variables A, B, C, D, and E. So A, B, C, D, and E. So now N1 series N2 in the pull down in parallel with. So N1 series N2. So N1 series N2 in parallel with N3 series in parallel with N3 series with N4 parallel N5 in series with N4 parallel N5. This is my pull down network. So N1 series N2 in parallel with N3 series N4 parallel N5, and then we can have the inputs, okay, A, B, C, D and E. Okay, so this is our transistor level schematic. Now comes on chip area. So now we have to find the sizes. Okay, so we can first find the size of pull-up network devices. It's very simple now. As we told that all possible paths, all possible paths from output node to VDD must have the effective pull-up strength of P. Okay, so it should be P. Every path should have a size P. Similarly, every path from output node Y to VSS should have a path N. So we can see how many paths are possible. So the first path which is possible is this. Okay, this is path number 1. This is path number 2, and this is path number 3. Okay, so if we consider this path, then the sizes, I'll erase them. So it will be 2P, 2P. That means if we take this path, that is P3, P1 path, then because P3, P1 are in series and there are two number of devices, so we have to have the sizes 2P and 2P. In other words, if we suppose if we take the path from P3, P2, then again two devices are in series. In that case also it will be 2P, 2P. The point. Okay, but if we take this path, that is P5, P4 and P2, if that path is considered, then because there will be three devices in series, so we have to take 3P, 3P and 3P. Okay, so it is like that. So this is the sizing of pull-up network. So we have P1 with size 2P, P3 with 2P, 3P, 3P and 3P. Now you go to pull down network. So again in pull down network, same thing is there. The first possible path between output Y and VSS is N1, N2, and they are coming in series. That is why if we take this path, the sizes have to be 2N and 2N. Now if we take this path, so N3, N4, if we take this path N3, N4, then again it is two devices. So 2N, 2N and 2N will be there. Okay. So now, just like we discussed last time, we have to write down the devices here, their size value, and then WP, LP, WN, LN, area of PMOS, area of NMOS. Okay, so we have P1, P2, P3, P4 and P5. So we have P1, P2, P3, P4, P5. So and then we have N1, N2, N3, N4, N5. So P1, P2 have sizes 2P and 3P. Okay. P3, P4 and P5 have sizes 2P, 3P and 3P. So 2P, 3P, 3P. So all 5 NMOSs have sizes 2N. 2N, 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 2N. And again, we should always remember that P is equal to 3.75, N is equal to 1.5. So 2P will be 7.5, 3P will be 11.25. Similarly, here it will be 3, 3, 3, 3 and 3. Okay. And our process is 100 nanometer. That is why all dimensions are in nanometers. So we have 100, 100, 100, 100, 100. Similarly, all lengths are also hundreds in this case. And WP is nothing but this into this. So multiplication of these two columns, this and this, when multiplied will give me this. So it is 750, 1125, 750, 1125 and 1125. Similarly, here it will be 300, 300, 300, 300 and 300. Okay. So here the area of P1 will be WP into LP. So we have 75,000. We have 112500, 75,000, 112500, 112500. Similarly, here we have 30,000, so we have 1, 2. So we have 2 times 75,000 and 3 times 11,2500. So area is equal to area of pull-up network plus area of pull-down network. So we have 75,000 2 times. So we have 75,000 into 2 plus 11,2500, 11,2500 into 3 plus in pull down we have 5 devices. So we have 30,000 into 5, 5 into 30,000. So what we have is 150,000 plus 337,500 plus 15, 1, 2, 3, 4. So 637,500. So 637,500. This is the result now. This is how you calculate it basically. So now we go to second one. A odd with B odd with C dot D. A, B, C, D. So solution. F is equal to A odd with B odd with C ANDed with D is equal to A bar ANDed with okay. So this is P1 series with P2 series P3 parallel P4. Okay, so this AND has become series, this AND has again become series, and this OR has become parallel. So this is my pull-up network. So my pull-down network will be N1 parallel, N3 parallel, N4 series, sorry, N1 parallel, N2 parallel, N3 series, N4 pull down network. Okay, so draw pull up network. P1 series. So we have P1 series with P2 series, P3 parallel P4, P2 series P3 and parallel P4. A, B, C, D. This is my pull-up network. And N1 parallel. So when we say N1 parallel, this is N1. N1 parallel with N2 parallel N3 series N4. N2 parallel N3 series N4. Okay, these two will come in parallel. N2, N3, N4. NMOS devices A, B, C, D. Okay. Now that the schematic has been made, we can start to putting the sizes. Very simple. So for this path, it will be now 3P, 3P. So if we are considering this path, that is P3, P2, P1 between Y and VDD, because three PMOSs are in series, so the sizes will be 3P, 3P, 3P. And if you consider the part P4, P1, then again they are there, so then you have to calculate it. Okay, so you have to calculate it. So there are two ways. Either you can take the path P3, P2, P1 and conclude it is 3P, 3P, 3P. But then now, if you take the path P4 and P1, then already 3P has been defined. So another way would be that you first consider the path P4. That is advisable. Why? Because 3P, 3P, 3P. So because the value of P is larger than N, when you say 3P, it becomes 11.25. If you take 3N, it becomes 4.5. You understand this thing? So P is equal to 3.75. N is equal to 1.5. So when I get a size as 3P, then 3P size value becomes 11.25. On the other hand, if I get 3N, it becomes only 4.5. That is why we should try to see if the size of PMOS becomes as small as possible. Okay, so we have to see that if the size of PMOS is as small as possible because value of P is more. So if I consider the first path, that is P4, P1, then I will conclude that sizes are 2N and 2. Okay, this is advisable. In the first approach, it was 3N, 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 and then we had 3N combined with 2N. So now we are having 2N and 2N. Now we can calculate. How? See, this like this. So now see, like very carefully you have to see. So this path it is. I'm very sorry. It's not 2N. It is 2P. Okay, it's 2P and 2P. So now already got the size of P1 as 2P. If suppose I take this path, then what will be the sizes? So sizes of P2 and P3 will be same, but then how to calculate it? It's very simple. Okay, see. So assume that the sizes of P2 and P3 hmm, are 2x. Hmm? Are 2x. This is unknown. Why I'm telling 2x? So that I can attribute x and x here. Okay. So here 1 upon P is equal to 1 upon 2p plus 1 upon x, not 2x, it is x here. Okay, very sorry, it should be p. Okay, question number 3. Fine. So what I've done is correct. So p equal to 1 upon 1 over 2p plus 1 over x is equal to p plus x. Okay. So okay, fine. There is actually no need to do all these things. It was pretty easy. Yeah, very simple. 2p 2p, this has to be 4p and 4p. Let me see if it is correct. So 1 upon 2p plus 1 upon 4p plus 1 upon 4p. Okay, we missed out something. Wait. Oh, ठीक. But so 1 over correct. We are correct. Okay, fine. So initially we had 3p, 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 and like that. Okay, so that was better. And here we had 2p and x. Hmm. Okay. 3/2. Okay, got it. Okay, fine, got it. So in the pull down network, in the path n1, so this size is n, and it will be 2n, 2n, 2n. So got it. P1, P2, P3, P4, N1, N2, N3, N4. Size, size value, 3p, 3p, 3p. Three by 2p. So n, 2n, 2n, 2n. Size value 3p. So again we have p equal to 3.75 equal to 1.5. So 2.25 and 3.75 into 1.5. 5.625. Eleven 2500 into 3. 393750. 105000. 498750.